parameters simultaneously?
Oh, it's very simple. HRT, hydraulic retention, is just one pass. Right? One pass means it pass any molecule pass one time, enter, goes out of the reactor. That's HRT. Okay, that's a single pass system. No recycle.
It means soluble, insoluble, whatever materials.
And imagine there is no recycle. There is no activated suspend. Okay. Just imagine you have a vessel. You are feeding something in. You are taking it out. You are not taking it out. Okay, you put a hole somewhere. Okay, and the exit. Whatever you put in, the access automatically will slide out. You go out. Right? Because you have a hole. Correct. So this is a single pass system. And how long this particles remains in the reactor is called HRT. Mathematically speaking, how do you calculate HRT? You divide now. You have the term two parameters. One is this flow rate. That is the liters per minute or cubic meters per day, depending on the count. Okay, and then is the volume of the reactor. Right. So you divide the volume, not the volume, working volume. I'm saying the volume which the liquid inside. Correct. So this volume you divide by the F value, that is the flow rate. Right. And how it turns out to be, okay, let's see how we can do that. Generally we do that with dimensional acid analysis. So basically so this is, let's say, in liter. Correct? Here is the F. So this may be liter per hour. Correct? So this, okay, we divide this units. So basically the unit will be hour. Here the liter goes out. Correct? It becomes hour, and therefore this becomes a charge. And that defines any molecule, soluble or insoluble, for that period of state. It enters, and it goes out. So if your reactor volume, if you are working in the lab, you have a 20 liter working volume, correct? Let's say you are operating, let's say 15 liter volume, correct? And you are feeding, okay, let's say here is your reactor, you fill it, right? You have the pump here, okay, right? And this pumping will be correct? Let's say here is the hole, so we can drop it, okay? So whatever you're feeding in, you know that. So if you have 15 liter and let's say you are feeding it 10 liters per hour, correct? So the HRT will be 10 liter per hour. That means 1.5. Similarly, on a scale of wastewater treatment, okay, to research plant, you have a large volume. So let's say you have 100,000 meter to flow. Okay, that's it. To calculate now, we can calculate the reverse. I don't know how to deal with this. Because you have non-erasable. Oh, that's good. This is very good. So let's say you have 100,000 per day. Correct. And let's say if you want to have, okay, you want to have an HRT of 2 hours. Correct? So now to calculate, now what you require? You require to calculate the volume of the reactor, okay, or the tank where you are going to treat it. Okay. So I told you the formula. Okay, here is the V divided by F is the HRT. Correct? Simple. You know the F here, you know the HRT. So basically V equal HRT multiplied by F, which is nothing but 100,000 to the power 3 multiplied by 2. So that means the reactor volume required is 200. Correct? The simple design. Now this is the working volume. Okay. In order to operate any reactor, whether actual sludge or tank, anything, is the working volume is always 70% of the total volume. Correct? So So basically, the total volume of the reactor is normally equal to working volume multiplied by the working volume is equal to multiplied by 0.7, or this divided by, so total volume will be
working volume divided by 0.7.
Here in this case, it is 200,000. So it will be roughly, we are engineers, we always have a round term, we don't go exact, because when you operate also you have difficulties. So we will go and have 300 to the power 3. That's the volume. Now this is the volume required. If I have a flow rate of 100,000 cubic meter today, so if there is a rain, there is runoff, we call it runoff. So what will happen in that runoff? All of a sudden a lot of water will gush into the sewer line, okay, and that will pass through the wastewater. You cannot, like in India, the operator cannot open the side line, let it go. Okay, no, he has to pass through it. Depending on, okay, sometimes it is also diluted. Okay? Because if it is diluted to an extent that it is the COD is below 10 ppm, then he can let it go. Because then there's a problem, it follows the norm. But he has to, otherwise he has to pass through its time. So now what do? We calculate the total flow, or the maximum flow and the minimum flow. Okay? There are times there is a maximum flow during the storm or during the rainy or whatever is that. We estimate that volume. What will be that maximum peak flow? Okay, and that peak flow is used as F. And then this reactor is designed. So that's the one way. And also we take into account, let's say after 10 years, like Delhi city is going so fast. Okay? Every year there are addition of I don't know how many millions, probably at least a couple of lakhs of people, correct, every year. So when you are adding those couple of lakhs of people every year, so they will do activities, right? They will use water, they will use everything, okay, whatever for the life is required. So that means that will increase the flow. When you increase the flow, how you're going to cope with the wastewater. So you also take that into consideration. And the same thing down the line, because it is not one single. There is the whole process units. If this is affected, this is changed, then everything down the line will be affected. So that also has to be taken. So you start calculating from this, and then you go down and down and down to keep that. Okay, what will be the minimum? What will be the maximum? Then you come out with a. This is a long procedure, so it's not that easy. But in a how do you say that? In a global way. In totality. Yes. Go ahead. Keep him quiet.
What is bioelectric?
Sorry?
What is bioelectric?
Oh, my goodness. Okay, it's a bioleaching process. That's a French word. It's basically metal bioleaching, but we talked this before. It's actually metal leaching. Bioleaching means mediated by bacteria. Like we talked about phenoxidine, bacillus thiopside, sulfur oxidizing bacteria, iron oxidizing bacteria. So because it is mediated by biological or the microorganisms, that are biology, so it's called bioleaching. In French, it is called biodissociation. I'm sorry. Yeah, please go ahead. Introduce yourself so that I know who you are.
I'm Muni.
Sorry?
I'm Muni. I'm a 5th-year student, PhD student of Professor Tyagi.
Here in JNU.
Yes, sir.
Ah, yeah, okay, morning.
सर हमारा क्वेश्चन ये है कि जब हम स्लज से मेटल को हटाते हैं, मेटल लीचिंग करवाते हैं और देन स्लज को यूज करते हैं इन एनी फॉर्म अदर इन एग्रीकल्चर और इन अदर वे, तो जो मेटल है वो अल्टीमेटली रिसाइकिल तो नहीं हो रहा है, इट गेट एक्यूमुलेटेड विद टाइम।
हाँ, स्लज में
स्लज में नहीं
Somewhere.
वो तो
Yes,
अल्टीमेटली
okay.
एनवायरनमेंट
चलो
में
आगे
ही
चलो,
है
हाँ, ठीक है।
तो वो तो अल्टीमेटली एनवायरनमेंट में ही है
हाँ।
इट मेक आउट योर प्रॉब्लम फर्दर
Okay, good question. Everybody understand the question? Yes. Let me see. Okay, probably I had something like this. So why I did not talk about this? Let me see. Check my few slides. Answer the question. Okay. This is the metal, right? Okay, I gave you another one which I was supposed to discuss today, but did not discuss. We'll discuss it tomorrow, and we will have the answer there. Okay. Yeah, here. Anyway, we'll discuss it tomorrow, but we can talk it now. Here is the answer of the question. Correct. So basically, what you have when you have done the mechanical leaching, okay. So you have now the metals in the solution and the solids in suspension. So you separate the two by centrifugation or by filter press. So metal will pass into the solution and the sludge will be retained on the filter. Correct. So now the metals are in the solution. Now there are two ways to do it to get rid of the problem. Because as you said very rightly, metals are metals, they're going to stay wherever they stay. They're not going to finish, like the pathogens, they die and okay, fine. So when we do that, okay, either we precipitate from the leachate, we call that leachate, the supernatant, okay, and then have a precipitate slurry, and that slurry you take it and dispose it securely. It's very small in amount, very small in volume, and you can go and put it in a secured landfill. Correct? So that's one way. But we have developed a process here to remove those metals and to isolate those metals. Okay? And here's the flow scheme. But behind that there's a lot of research. And one of my students, they did his PhD on that how to isolate those metals. Okay? And he developed a thermodynamic model, not the mathematical model, but a thermodynamic model based on the solubilization or the equilibrium constant in solution and in the precipitates. And then he determined the optimum condition for solubilization and precipitation of each metal one at a time, or the sequential. So you go with certain pH and then you keep on slowly reducing the pH at certain values. Some metal will precipitate, then remove them, go to another one, remove them. So like this you can precipitate and separate those metals. But as a lump parameter here, so you have the leachate here. So you have the leachate here, okay, and this is the balance what Manish was asking me. So 4,411 meters. So what you add basically this percol to 757. This is the name of the polymer, and this is an ionic polymer. Because metals in solution, they are charged positively, so they attach to the polymers, negatively charged polymers, they form the complex, and they precipitate by themselves. Okay? You don't need to add any chemicals like sodium hydroxide or sodium carbonate or calcium oxide, something like that. So basically, and then these polymers, the flock size grow, and then they can decant. Okay? And then you have the metallic sludge. We call it metallic sludge because the organic matter is very small. Okay, in them, probably maybe 1%, not more than that, or 2%. This is totally metallic sludge. And then you take the metallic sludge, and so here is some composition of the metallic sludge in that. Okay, so you have that, and then you can dry, dehydrate. Dehydrate means that dry the metallic sludge, and that metallic sludge you can use to isolate metals. Or this sludge you can also dump into the spill. So that's how you get rid of metals. But at the same time, the supernatant also contains some metals, and I'm looking at the composition here, but I don't find it. No, it is not here. Okay. So I cannot tell you there right now, but I can always get back to you with that composition. So what happens, sorry, in the supernatant, after the precipitation of the metals, there are some still residual metals because you cannot remove 100%. Correct? So what do we do that? Okay, means that whatever the supernatant is left after this metallic sludge, you send back into the treatment unit. And when you send the treatment back to the treatment unit, okay, on the top of your secondary sludge, activated sludge process. So these metals, along with the other influent metals, they will get absorbed into the sludge, and then they are recycled again. So that way you can develop a dynamic equilibrium, and that will control the metal concentration in the activated sludge as well as in the sludge finally. So that's the only way. But nowadays also the technology is being developed, so-called the electrocoagulation. Okay, and that is where you use the known electrodes, a certain electrolyte. You can also separate those, especially those important metals. And the important metals are copper, manganese, of course, zinc and lead has low value, but certainly copper and manganese they have good values. So you can see. On top of that, leachate will also solubilize some of the nitrogen and phosphorus. And so when you separate, when you have this leachate, 4,400 liters, so you will also have those NPK material inside that. And that concentration is maybe fairly quite substantial in terms of the disposal. So basically, you cannot consider to dispose that supernatant like that. So that also then you return back to the treatment unit. So that NPK, nitrogen, phosphorus solubilized, and potassium which is solubilized will also again will be recycled and used by the microorganisms in the same way as the metals. So that way you can enrich the sludge also in terms of nitrogen and phosphorus. Or you can do other things because that depends on nitrogen is in good form. Okay, if it is in ammonia form, then you can also precipitate so-called S2-white. I don't know if you ever heard the name S2-white. S2-white. Oh, we will have somebody in discussion on this. I remember exactly. This is potassium ammonium sulfate. Don't remember the exact formula. Ammonium phosphate. And what it is, I don't know if you have seen sometimes there is a droplets in the CO1. It's a piping. Have you seen that? I found really very thick crust on that. And if you give a 1 ton of hemp, you can break it. It's so hard. That's nothing but this. So basically, the leachate or the supernatant after recovery of metals, it also contains ammonia and of course it contains a lot of phosphorus. So what you can do that, but if it's short of the magnesium ammonium phosphate or potassium ammonium sulfate, so you can add some magnesium to that. And that magnesium added will precipitate this magnesium ammonium phosphate. And that magnesium ammonium phosphate crystals, and they are the crystals, so they precipitate an idea, and you can recover that. And that's a very good fertilizer, very good fertilizer. The most important advantage of that is it's a slow release fertilizer. That means it stays in the crystal form when you put it in the soil. It stays in the crystal form, and the nitrogen is released and phosphorus is released very slowly. So what happens? And the plant uptake is always slow because plant growth is not very fast, right? So whatever is released, so it is basically release mechanism is like this. So you will not waste your nitrogen phosphorus. So in case of when the high rain comes, there is a flood or there is something a storm. So this nitrogen will not be washed out because it is in the crystalline form and it will exist there. So that can be also done. Of course, it's not very expensive commodity. It sells roughly $1 kilo, 60 rupees a kilo. Probably 60 rupees is very expensive in India, but I'm not sure what is the price of fertilizer here. But it's quite inexpensive. Inexpensive fertilizer. So it is with the reach of farmers, and farmers are very happy. And because we have a big problem of surface water contamination and as well as the groundwater contamination. So in our situation, it is very, very good proposition because it doesn't solubilize as fast and the excess nitrogen does not pass through the ground to contaminate the groundwater, which is very good. Next.
So in this slide, when after the after the using that anionic polymers, the concentration of like other elements are decreasing, but the nickel concentration remains same like here Mg per liter.
Alcohol and decanted metallic sludge.
Effluent contains same concentration of nickel as initially what leachate contained.
That one?
Yeah. Nickel is 0.24 mg per liter, and here it's the same mg per liter. So maybe
Copper is 2.7, copper is 19.3, and the chromium is 0.1. Chromium is okay. So probably okay, I reversed, but I was putting the value, which is possible because copper is 19.39 milligrams per liter. So here copper is 2.7. So basically here should be less. So basically what has happened with this normally that should not be the one. Actually no, that's not correct. Here is come down to this side.
Yeah.
Copper is 2029. So basically this is the metallic sludge.
metallic sludge.
Okay. And that one is the supernatant.
Okay.
That's the supernatant. And that one is the influent. That's the leachate.
Leachate.
Yeah. So a leachate, let's say per se copper. Copper leachate concentration was 19.39 milligrams. So when it comes down to the sludge, so copper is 2029 milligrams per liter, or milligrams per kilograms. Okay, so it's increasing. Whereas it is decreased, copper from 19 to 2.7 milligrams per liter. So that's a decrease there. So that one is okay. So these arrows are not incorrect. So basically they should be the opposite way. Okay. Sorry, those arrows right now. Correct instead. Okay. So you can correct also in your. I cannot correct it because it is a transported diagram from somewhere. Okay. So you can correct in your correct in your. So the first is the influent before the metal precipitation.
That's mg per kg is a leachate.
No, mg per kg has to be metallic sludge.
Metallic sludge.
Leachate was there on top, and the supernatant after removing the metallic sludge is the effluent. What is not correct? It's the effluent. That's right. Is the supernatant or effluent? So that will go up, and that you will return to the wastewater treatment plant. That's correct. There's no mistake. Everybody is correct? Everybody is with me? Or not followed? Okay, good. Sorry for talking about it. Yeah, go ahead. चलिए जल्दी. How come no question? When I asked you question.
Sir, actually you told us that in the municipal treatment plant the denitrification process is slow. And
Can
we
you speak a little bit loud or you come here in front?
so sir,
Because there's some problem in my ears today.
actually sir, you said that in the municipal treatment plant the denitrification process is slow.
Yes. Yes. Okay.
And there is as such key there is metal removal or something process, but how the municipal people cope with the denitrification process? Either they depend solely on bacteria or they apply something different to get the excess nitrogen removed.
Okay. Good. Everybody understand the question? No, they always depend on denitrification by bacteria, because that's the cheapest way and that's the most convenient way, and it is applicable also, and it is controllable. But then the plants which operates in nitrification process, they are specially designed. They are specially designed for longer HRT, for longer hydraulic retention time and the longer sludge phase, because you have to retain those slow growers, denitrifiers.
Because we have to give them more time to flourish.
You have to give them more time. At the same time, you have to give them more substrate.
Substrate, okay.
Right.
Definitely.
So because heterotrophs, they grow very fast and they will consume. Okay, it's a competition. It's a competition here. Like, okay, just simply, okay, many people are fighting for small food. Okay, so those who are the strongest, they will capture, or those who are faster. Correct. It's the same thing. And then, if nothing is left for the denitrifiers, then you will have the nitrite in your system. Okay, so then you have to design, or you have to see in such a way that all the substrate is consumed, but some is left for the denitrifiers. If the need arises, okay, that substrate is all finished and the denitrification is not done, then you have to supply more carbon.
It is not.
Then you are left with no alternative. Of course, it is expensive, very expensive, because then you have to supply them, depend on what type of carbon you are supplying. And or sometimes the denitrification can be carried also in the second reactor if the situation is uncontrollable. But normally in domestic wastewater treatment plants, this situation never arises. This situation arises only in case of while treating the fertilizer. They have to feed the substrate, otherwise nitrogen will pass through the system.
Exactly, and then it will pass the limit.
Then you will have more problems because nitrates are more deleterious to the
Yes.
Good question.
Sir, one question.
We have talked about the biofilm.
Yes.
We develop biofilm in that. To purify.
The wastewater treatment
For biofiltration. The film will be developed, will be formed by bacteria itself, or we just do something more.
No, I didn't get it. You mean are you saying that the biofilm will automatically develop by the bacteria?
Exactly. Yeah.
Or we have to enhance the biofilm formation?
Exactly that.
Okay. No. Answer is no. No, we do not enhance. But the bacterial mass, okay, they themselves will develop the film around the inert material. Okay? Now, the mechanism of biofilm generation is through the formation of so-called the compounds, protein carbohydrate compounds, which are called the extracellular polysaccharides. And most of the wastewater treatment bacteria, they have the capacity to generate those polysaccharides. I think I will talk some of that if time permits me. We'll talk about that. And these polymers, they help in the formation of the film. Okay? So they are sticky material and they can stick on around of the inert material, and then bacteria can stick into that. Okay? Basically, they are in the film. Okay? And that grows because they keep on producing these EPS, so-called extracellular polysaccharides, and that keeps on building the film. In fact, the film keeps on increasing. It's on the spherical the particles, and the film keeps on increasing all sides. Ultimately, it comes to a level when the hydrodynamics of the reactors, hydrodynamics mean the flow and the agitational level, flow speed, agitation levels, the viscosity. There are so many factors which determines the hydrodynamic characteristics. Sorry?
It will also affect the.
Yeah. So based on those, okay, the film comes to a certain level, and then it will start breaking by itself, which is we call it sloughing. Okay? So the sloughing will occur, and that way the level of film is controlled.
But sir, one more thing, sir. At this stage, sir, I want to know just because as we know that the EPS substance, they have the capacity to just capture heavy metal type of
also
thing. So if and you said that if we just from opposite side we just apply pressure and it again we just get rid out of film. So in spite of doing this, if we collect the film, so it might be possible that we can get some sort of metals there.
of course, that's the
Exactly. So we can initially separate out that thing, and that EPS type of material can then be again used. For, I think, this type, recovery of metals, and then after recovering the metal, the polymeric substance which will be left can then be used for flocculating some other types of.
Exactly, I will talk about this when I discuss the biodiesel chapter. Okay, the biodiesel from the slabs, I will talk about this. Okay, this is a very good point. Every one of you understand what is the question? Who does not understand this question? Very important question is asked. Someone here, nobody understands? Okay, everyone understands. Okay, yes. Okay, when you take out, okay, number one, the sloughing. Let's start from the sloughing. Okay, when the sloughing occurs, so everything will break down from the plate, including the EPS, bacteria, and whatever is there, metals or anything else. There may be toxic organic compounds also in the film. They might also absorb. So everything will break. Okay, when you do the backwashing. Okay, and then on the other hand, the backwashing, you collect this material. And this is nothing but the sludge. Only thing is that instead of 2 grams per liter, you may have 10 grams per liter, 5 grams per liter, depending on how much was the film built. Now this sludge is there. Everything is there, metal is there, microbes there, EPS is there, and whatever is there is there. Okay. Yes, there is a process, okay, and we also have done a lot of research on that issue, and we can extract that EPS, and these EPS are a very good flocculants. We were talking about the polymers here. We discussed about that.
In spite of this polymers, we can.
Somebody was asking me here the question: how do you separate liquids from the sludge? Okay, student is not here, but all she's there, so good. So why do you people sit there? Yeah, there's a lot of time just there. So anyway, we'll discuss that in that chapter. Okay, probably.
And so the polymers which are used to initiate the biofilm, they're synthetic or the biopolymers?
No, you're Neha, right? I didn't get
I'm Khushbu.
You're Khushbu. Khushbu, no, I didn't understand it.
You said that to initiate the biofilm formation, we use polymers.
No, I didn't say that.
Biofilters.
I'm to just mesh and the bacteria will stick onto it and it will just.
So,
Bacteria itself.
Alright, okay.
yeah.
To initiate, we just do simply nothing. What do? You fill it into the reactor, and then there are bacteria. You inoculate with the activated sludge. To form the biofilm to start with. Okay, the reactor. You fill the reactor with your wastewater, and you inoculate the sludge, and then you have this material. The material there, spherical material, or maybe cubical, whatever is there. You can put it there, and then start extracting. The microbes, they will start growing. Correct? And the molecule, when the microbes start growing, they will automatically start attaching to this material. And with the time, and then the COD will decrease, and then you start feeding it in a continuous way. But you run batch wise, and then you start feeding it. Okay, and then controlling like a continuous reactor. Okay, and then the biofilm will continuous growing. The stage will come, that it will grow, and then you will need a backwash. So it's basically you don't add anything, no polymers. The microbes they do the job very perfectly by themselves. They are very intelligent. They are very, very intelligent.
But the role of CN ratio is also came in picture during
well,
the
there are so many
formation
factors. If you are talking about, I don't know,
biofilm
we are studying, we are trying to explore the EPS. Yes, okay. There are so many factors. Okay, like any other process. C/N ratio and no, but okay, C/N ratio can affect the composition of the EPS.
Composition of
Because what are the EPS basically? Is everybody with us here?
Yes.
I don't want to get lost. There's people here in this discussion. Okay, when you change this carbon nitrogen ratio, so the composition of the EPS produced will change. Okay. Now I was telling that what is basically EPS? These are the carbohydrates, the proteins, the DNAs, and there are the other cellular material. Now, if you have very high carbon content, less nitrogen content, so that will reflect in EPS also, you will have a higher carbohydrate concentration. If you have C/N ratio low, that means high nitrogen, that will also reflect in your EPS. Now, but if you are trying to produce, as you said, that by as a good flocculants, of course, they are very good flocculants. So if you are producing EPS, because in sludge, okay, they do, in wastewater treatment, nothing is controllable, everything happens by itself. But if you are producing EPS as a bioflavonoid, then you control the CYN ratio because you want the higher concentration of the protein moiety in your EPS. Why? Because there are certain groups, okay, especially the sulfur containing charge and group, because group charge is on the groups. So basically, then you create the groups which can create the positive charge, because then you can use as a cationic bond. Because if you are using as a flocculant, if you want to use them as a bioflavonoids, then where you want to use them as a bioflavonoid? That's interesting. If you are using, okay, just to attach the metals, like you said, you attach the metals. They are very good material to attach the metal. Then you need the higher carbohydrate moiety, because then you need the more and more negative charge, because metals are positive charge. But if you are using as a flocculant, what material you want to flocculate? If you want to flocculate back the sludge is negatively charged. So you need the high positive charge on your EPS. So then you have to see that if you are manufacturing separately, not as activated sys process, then you can control your CN ratio or nitrogen content or whatever. Sometimes you can go the other, okay, in the form of nitrogen also affect that, and then you can get the high nitrogen content in EPS. And then you can measure the charge. You will get surprised. We have a lot of research. We have a lot of publication on that. Okay? And anyway, I will give you some talk, but I will not go to those details here because I don't think so. We will have that much time to do that. But yes, if time permits, we can keep on talking in 1 month and we can keep on discussing. I think 4 or 5 students have done PhD with me on the EPS subject.
Okay.
Currently, there is one
of my general question, like during a starve condition, when film will get break or by
that one grows.
yeah. So the EPS material act as a bioflavonoid. That material will be also consumed by bacteria because because this is composition having carbohydrate and protein, so they can directly use that excretory material for.
Everybody understand that question? Right? Is there anyone not? Okay, yes. Now, first of all, you have to go back and think about why the bacteria should synthesize EPS. Why? It's an extra carbon. The microbe have to do extra job. They have to synthesize. They have to spend the energy. Okay, energy to produce that using fermentation, and then they synthesize these components. Why do they do that? Basically, number one, it's a safety mechanism. And the bacteria synthesize in inverse condition. And when we consider, for example, the metals are toxic. So when there are metal concentration in solution, bacteria wants to protect that. As I said, they are very toxic. It's an automechanism. And that's why they synthesize these EPS. And EPS, okay, protects them, it absorbs the metal immediately because they are negatively charged. So the metal is now bound. So it doesn't harm it.
Immobilized.
Correct. So it's good. The bacteria is safe. Secondly, when if the system having the bacteria having the EPS in the system is starved, certainly they will start consuming a part of the EPS, but not all EPS they consume. But certainly there are studies on that, and not many, but certainly there are few studies where they have proved that the EPS serves as a carbon source as well as a nitrogen source under the so-called fanning. They can go back and use that.
I think that we can close it now.
Sorry?
So now we can go to the...
Oh, it's already time over? Oh my God, time flies. I thought it was only half.
Okay, so now after this tea break, we will go to the JNU-STP. Okay. So how you will go? Tell me. This is the question.
Work करते हैं.
Work करते हैं, of course. I have a car, and also Khushbu, you have a car. तुम ड्राइव खुद करती हो? दो चार को तुम देखो जो करेक्ट
कंप्यूटर वो करते हैं ना, सब वो करते हैं.
जो स्ट्रॉन्ग है वो सीधा चले जाओ सीधा. नीचे यहाँ जो है ना बस स्टैंड के ठीक नीचे, के पीछे आप नीचे जाओ, ऊपर आ जाओ. ठीक है. और जिसका वहाँ जिस हॉस्टल में उधर रहते हैं, चाहे तो आप वहीं रहते हैं. ठीक है. थोड़ा सा खाली पे जिससे एनर्जी मिल जाएगी.
And the carbon concentration is very, very low because the fertilizer industry will not have any carbon almost. Or the carbon will be in the form of hydrocarbons which are B grade also. And it is possible that D95 material will not be able to degrade those. So there the need may arise that you have to build extra input to the substrate. And that's an advantage. Nowadays, okay, because these denitrification procedures are also conducted in so-called the sequencing batch reactor. Because the active resistance plant was established since 300 years, they started working on that. So nobody wants to dismantle them now and scrap and put the new technology, because now everybody has this new technology, specifically the sequencing batch reactor, which is very efficient in removing the phosphorus as well as the nitrogen, especially the phosphorus. And the new plants are being built up on that sense. Nobody builds up nowadays active resistance plants, but what has been built up, they are built up. At least in that part of the world where I come from, or where I come from India, and I live in Canada, where I live in that part of the world, the people are not constructing any of the active resistance plants. But they are operating because they are there in the place. Correct. And if the need arises of the deficiency of the substrate,